So you got time to do your recommended assignment. Okay, we're almost finished with this unit. So today we're gonna finish up the notes. Tomorrow we're gonna do some practice. We're gonna review and then test. I would prefer us testing on Wednesday since now they've screwed up our Thursdays. Yeah, like the Pride schedule. Like now it's Lion time on Thursdays. So that makes our Thursdays really short. I would like for you to have more time. Yes. Huh? Um, let's do quiz Wednesday, review Thursday, Friday test. Everybody good? Okay. I hate to do that like the weekend before homecoming. Thoughts, questions, concerns? All right. So let's go ahead and get started. We do next lesson. We did. This is part 2. This should be day 2. You should say day 2 up at the top of your paper. What? No. Did I print the wrong one? No way. I did print the wrong one. 20 seconds. Okay. So we are trying to find out, are the events yes taco tongue and yes evil eyebrow independent? Okay. So the question is, are they independent? Okay. We're going to use some data from the previous lesson. I'm just going to give you that data because we've got more people today. Okay. So we're going to put 15 that can do both yes taco tongue and yes evil eyebrow. We're going to do 5 can taco tongue but no evil eyebrow. 3 can yes evil eyebrow, no taco tongue. And 7 can no evil eyebrow and no taco tongue. So if you weren't here last time, evil eyebrow is where you like have one eyebrow that goes up and then one that doesn't. And then taco tongue is where you like stick your tongue out and you kind of like fold it in half and it looks like a taco. Okay. If you can't do either one of those, you need to practice. Okay. So what is the first thing we do when we have two-way tables? You add up the totals on the sides. Okay. So 15 plus 5, 3 plus 7, and 5 plus 7. And everybody pauses. 15. Why is that one the one that everybody's like glitching? All right. 15 plus 3. There you go. And then 20 plus 10. All right, cool. So we always add up our totals on the side. That's the first thing that we do. Okay. So suppose we randomly choose a student from class. Given that the person selected yes, evil eyebrow, what is the probability that they are yes, taco tongue? All right. So this word given is really, 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 really important. Okay. Word given is really, really, really important. All right. So with that being said, given that the person has selected yes, evil eyebrow. So out of the yes, evil eyebrow, so out of the 18, how many would have said yes, taco tongue? 15 out of 18. Okay. Which, if we put that into our calculator, we're going to get 0.833. So that would be 83.3%. Okay. If we wanted to write this out in mathy way, then we would say the probability of yes, taco tongue, given, so that line is given, yes, evil eyebrow. So again, the way you read this is probability of yes, taco tongue, given yes, evil eyebrow. Okay. Now on B, it says, given that the person selected no evil eyebrow, so out of the no evil eyebrow, that would be 12. What is the probability? Yes, they are taco tongue. Well, that would be 5, right? So 5 divided by 12, that's going to give me 0.417. That's 41.7%. Can you write it as a math way? Can you write it with the probability of no, I'm sorry, probability of yes, taco tongue given no evil eyebrow. So again, probability of yes, taco tongue given no evil eyebrow. The line means given. What? He is probability. Good morning, sunshine. All right, so these are what we like to call in the stats world conditional probability. Okay, so these are what we call in the math world, stats world, conditional probability. Okay, so whenever you see the word given, that's conditional. Okay, so based on your two previous answers, what conclusion can you make? So let's look at this. If they say yes, evil eyebrow, then yes, they can taco tongue 83%, right? If they say no evil eyebrow, they're going to be about 41% taco tongue. Okay. Right? So based on that, what can you say? Go ahead.
Are able to are more likely to able to do.
People who can evil eyebrow are more likely to what? To be able to taco tongue. Than those who can't evil eyebrow. Okay, so independence is if knowing whether or not one event has occurred does not change the probability of the other event occurring. Okay, this is really important. You have to know this guy. So if knowing whether or not one event has occurred does not change the probability that the other event will occur. So are the events yes, taco tongue, and yes, evil eyebrow independent? Are they? What conclusion did we just make? Right. Okay. Okay, so knowing whether a person can evil eyebrow does change probability they can taco tongue. Okay, so they're not independent. Okay, they do impact each other. All right, go ahead and flip the page. Okay, go ahead and take a moment. Go ahead and see if you can do A, B, C, D. Go ahead and try A, B, C, D. Yep. You may go back. Okay. All right, try A, B, C, D. All right, so I already did the totals for you. We've got data for seniors at this high school. Find each of the following using the values in the table, right? As a fraction, a decimal, and a percent. Okay, so what's the probability of getting taco tongue? Okay, and how did we get that? Okay, so we said 480 out of the 600. So 480 divided by 600, and that's going to give us 0.8, which is 80%. Okay. What about yes, taco tongue, given yes, evil eyebrow? So when we say given, we're going to look at the bottom being the total of evil eyebrow. So out of the total evil eyebrow, how many are taco tongue? 180 out of 200. And that's going to give us 0.9 or 90%. On the next one, given no evil eyebrow. So out of the no evil eyebrow, that's out of 400. How many can taco tongue? 300. So 300 divided by 400, that's going to give us 0.75. That's 75%. Okay, so are yes, taco tongue and yes, evil eyebrow independent? How can you tell based on this data? Is there a difference between these two? Yeah, about how much? Okay, so is that a big enough difference to say, hey, are these dependent or independent? Okay, so are they independent or are they dependent on one another? Dependent, right? So again, they're dependent on one another. If I can evil eyebrow, I'm probably more likely to be able to taco tongue. Okay. So we're going to talk about actually how to prove that in just a second. Okay. Say that again. We all good back there? All right, let's look at the next one. Suppose the ability, taco tongue and evil eyebrow are actually independent events. Determine the following probabilities. So the probability of yes, taco tongue was 80%. We already talked about that one. What is the probability of yes, taco tongue and yes, evil eyebrow? That's 80%, right? We did that one earlier. That is 90%. But if they were independent, pause. If they were independent, what should that mean? Right. So then we should get 80% here. We should get 80% here. If they are independent, these all would be the same. Okay. So if they are independent, all are the same. Okay. So really quick, this is probability of A. This is probability of A given B. And this is the probability of A given B not. And they would all be the same if they were independent. Go ahead. If they are not equal, when we do these three things, then they're not independent. Does that make sense? So they have to all be equal. That way they don't impact each other. Yeah. Okay.
But how can the same thing?
So if they're independent, they're not influencing each other. because it shouldn't matter. Then that means our data is proving that they're dependent. We're going to have an example of that in a second. Okay. Really quick. So these are my three. That means that if I have probability of A, it should equal probability of A given B, which should also equal the probability of A given B not. All three of those have to equal. Okay, so kind of like what David just said, well, what would our data actually look like? Well, let's take a look. On here, it says, here are our totals. Okay, now we want to fill in here. We said that we want to have 80% of the yes evil eyebrow be able to yes taco tongue. All right, so bear with me on this. Out of the evil eyebrow yes, we want 80% to taco tongue. So what's 80% of 200? 160. So we're going to fill in 160. So if this is 160, how much is going to go here? Okay, everybody good so far? The reason why I chose 80% is because that's what we found up here, right? Okay, out of the no evil eyebrow, so out of the 400, how many, what's our percent? Okay, so our percent is 80%. So that would be 320 would go here for yes, taco tongue. And that would make 80 be in this last row. Okay, so David, this is now their independence. These are the results that we should get for that. Does that make sense? Okay. So how can you tell from a two-way table if two events are independent? You're going to check the conditional probability of one event and whether it stays the same given whether or not, the other event occurs. So basically, here is your event. You need to test whether or not that event occurs given the other event. Okay. For those of you who are visual, you're using that formula. So you're going to check conditional probability of one event if it stays the same given whether or not the other event occurs. Like, give me 1 second. Like, not like a question. What we had talked about. Okay, conditional probability. Okay, and this is the probability of one event given another. Okay, you're gonna see this formula. You're gonna see probability of A given B is equal to the probability of A intersection of B over the probability of B. Yes. Okay, so where they cross over that conditional probability. It's what we did already. It's just putting it in mathy notation. Intersection, so where they cross over. Think about like an intersection of two roads. Taco tongue and evil eyebrow. Okay. We also talked about independent events. Okay, so knowing whether or not one event occurs does not change probability of another. Okay, and we've already talked about this formula, but probability of A equals the probability of A given B equals the probability of A given B not. So if all of those are true, then they're independent. So the Pew Research Center randomly selected 100 mothers in 1976, 1994, and 2014 and asked them how many children they had. Two-way table summarizes the responses. Suppose we randomly select one of the survey respondents. Define events have 4 or more children. S is 1976, N is 1994, and F is 2014. So find P of C given S and interpret this value in context. Okay, so what are they asking us to find? Put this in words. Okay, good. Okay, so when they say interpret, that's what you're doing. You're putting it into context. Okay, so they told us these things. Okay, so when we interpret, we're going to say given that the mom was surveyed in what year? Okay. There is and we're about to find the probability. She had how many children? 4 plus children, right? Okay. So out of the people in 1976, how many had 4 or more children? 40. So 40 divided by 100 is 40%. We're going to leave this actually as a decimal. I lied. Let's leave it as a decimal because we need that for the next little spiel. I would, because we're about to start talking about like p hat, this, that. You're going to need that. Yeah. We're not there yet. It's taking a little bit of time. I got you. Okay. Given that the chosen mother was not surveyed in 1976, what's the probability that she has 4 or more children? Write your answer as a probability statement using the correct symbols. Okay, so when they say symbols, they're talking about like something like this. So given that the chosen mother was not surveyed in 1976, so we're going to say given was this line, and 1976 was represented by this S, but we want not 1976, right? And what are we trying to find? What's the probability she has 4 or more children? What symbol is that represented by? C. So we're saying the probability of C given S naught. Okay, so how much is that? Let's take a look. So S naught, that would be 1994 and 2014. So how much would that be together? 200. So out of the 200, how many had 4 or more children? 26, because we would do 13 plus 13. Okay, when we plug that into our calculator, we're going to get 0.13. Okay. Okay. So are the events surveyed in 1976 and 4 or more children independent? No. Why? Okay. So coming down here, we would say no, and we would say P, the probability of C given S is not equal to the probability of C given S naught. Okay, so again, we would say no, they're not independent. And the reason why is because we would say C given S is not equal to the probability of C given S naught. Okay. So we would need to interpret what that means. So we would say mothers surveyed in 1976, are they more likely to have 4 or more children or less likely to have more children? Okay, 1976 are more likely to have 4 or more children than moms not in 1976. So back to the Starburst. So if you weren't here Friday, you missed out. The game is simple. Reach your hand into the bag or a cup. Choose a Starburst. Each cup has 4 red and 2 yellow. Return the first Starburst into the bag, mix up the bag, and reach in for another. If the color matches the first, you win. What's the probability of winning? Okay, so we talked about this the other day. Are the 2 events, the first is red and the second is red, independent?
Yes.
Wow.
So same probability of pulling a red, given you already pulled the red, putting it back in the top or the.
Okay, so knowing whether or not the first is red does not change the probability of the second. Yeah, but it's still the same probability either way because we have 4 out of the 6 are red. And then on the next time, we have 4 out of the 6 are red. So same probability each time. They're independent events. Okay. All right. So for independent events, P of A and B, that equals the probability of A times the probability of B. We did that last time. Okay. So really quick, if the probability of the first one is red, that's 4 out of 6, right? And what's the probability of the second is red? That's 4 out of 6. Remember, whenever we see the word and in between 2 things, we're going to multiply. And that's going to give us 16 out of 36. Okay. The probability of first is yellow. That's 2 out of 6. And the probability of second is yellow. That's 2 out of 6. So that would give me 4 out of 36. And that, again, that's what we did last time. But what's the probability of actually winning? Well, you win if you do either one of these, right? So that's 16 out of 36 plus 4 out of 36. And that equals 20 out of 36, which is 0.56. Plot twist. This time you're not going to replace the first Starburst before getting the second. Your group should play 10 times. Record your number of wins at the front of the room. Based on the results from your whole class, what is the estimated probability of winning this game? So you're going to draw, and then you're not going to replace, and then draw again. Record your number of winnings. You're going to do it 10 times. Each person is going to do it 10 times. Cool? Okay, once we finish this, then you can eat the Starburst. So once we finish. Okay, go ahead and get started. I'm going to give you about 7 minutes. When I added that up, I got 104. Can somebody verify that, please? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20. So out of the 200 games, we had 104 wins. That's what I got. Tell me what you got. Like me, because I did it on my iPhone, so there's no telling. Yeah, okay. So out of the 200 games, we got 104 wins. Okay, if we take 104 and we divide it by 200, that's 0.52. That's the estimated probability of winning this game. Okay. Now, I do want to point out something. When we say not replace, this is also known as without replacement. Yes? Okay. feel like I shouldn't have to point that out. That's good. So now we're going to actually draw a tree diagram to calculate the theoretical probability. So fill in the blank boxes with the correct probabilities as fractions. So when we start at the beginning, okay, and we do the red starburst, okay, let's say we draw and we got the first is red. What's the probability of getting the first is red? 4 out of 6. Okay. What's the probability of getting the first is yellow? Okay, cool. Everybody's good. Okay. Now, yeah. It gets switched. First is red.
Oh, yeah.
Oh,
Sorry. Oh, wait.
This, hey, this is supposed to be on that part. Yeah. You see it? Okay.
Wait, no.
Okay. Okay, so 4 out of 6, 2 out of 6. Everybody good? Okay. Hey, y'all knock it off. I don't see a pencil in either one of y'all things. Okay, let's say on that after the first is red. So given that the first is red, we're trying to find the second is red, given the first is red.
3 out of 5.
So now that's 3 out of 5 because we have one less this time. Okay, what would be the probability for our yellow though?
It'll be
How many yellows do we have? 2 out of 5. Everybody good? Okay. So let's see the probability of this happening where if the first is red and the second is red and we didn't replace, well, we would take 4 out of 6 and we would multiply it by 3 out of 5. And that would give me 12 out of 30. On this one, we would have 4 out of 6 times 2 out of 5, and that would give us 8 out of 30. Okay. Can you fill in this bottom row? So, if the first is yellow, we have a 2 out of 6. If the second is red, then that's going to be a 4 out of 5 chance. For yellow, if the second one is yellow, that's going to be 1 out of 5. Okay. Now, let's find the probability that the first is yellow and the second is red. So that would be 2. So the first is yellow, so 2 out of 6. Sorry. And 4 out of 5. That would be 8 out of 30. On this bottom one, the first is 2 out of 6. The second is 1 out of 5. So that's going to give us 2 out of 30. Okay. If you added these whole things up, so like if you would have added the 12 plus 8 and the 8 plus 2, that would give you 30 out of 30, which equals 1. That's how you always check your tree diagrams and make sure that they're correct. At the ends, they should all add up to equal 1. Yes. Yep. So 12 plus 8 plus 8 plus 2 is 30 divided by 30. Yep. Okay. So what is the theoretical probability of winning this game? You said 13 out of 30? 14 out of 30. So we would have the 12 divided by 30 plus the 2 divided by 30, which would give us 14 out of 30. Well, where am I getting those numbers from? That would be if you had a first red and second red, that would be 12 out of 30. If you had a first yellow and second is yellow, that would be 2 out of 30. That's where I pulled those numbers from. Okay, so that would give me 0.47, 47% probability of winning. Yeah. I can pull down the screen. Okay.
It sounded like either.
All right, go ahead and look at the next question. Go ahead and look at the next question. See if you can answer that one. So what is the probability that the first is red given that they won the game? So how do we do this? So out of the probability that they win, we're trying to find that they have the first is red and they win. Okay, so looking at our tree diagram, what was the percent or what was the fraction for when they got red and they won the game? The first is red and they won the game. 12 out of 30. And what was our probability of winning? That's our last problem. What was that? 14 out of 30. So if we take 12 out of 30 and divide it by 14 out of 30, that's going to give us 0.86. Okay. So let's talk about what did we just go over? Let's do. All right. So we went over general multiplication, which I mean, we've kind of seen this before so far, but the probability of A and B is equal to the probability of A times the probability of B. Okay, so again, if we're saying and, it's going to be multiplying. If we say or, it's going to be adding. And it's the probability of B given that we had A. Sorry. Okay, we've already talked about if they are independent, what that means. Y'all kill me. So if A and B are independent, then that means that probability of B given A, so probability of B given A equals the probability of B. So the probability of A and B is equal to the probability of A times the probability of B. You're given two formulas on your formula sheet. The only ones that you are given are these two. So we did the conditional probability the other day. This is just a reminder, you don't have to write this down. Okay. And then you also are going to be given this one, probability of A given B, such that you have the intersection of A and B over the probability of B. Okay. And we've talked about this. This is just the notation for it. Okay. The other thing that we went over today was the tree diagram. Okay. So the tree diagrams, when you draw them, you want to make sure that you have the probability of A and the probability of A naught. And that's going to turn into the probability of B given A and the probability of B given A. I'm sorry, probability of C given A. E. Yeah, that was the yellow. B would be that, like the second red happened. Okay, so what this turns into is the probability of A and B. This turns into the probability of A and C. Down here, down here, you're going to have A naught. So that's the probability of B given A naught, or the probability of C given A naught, which is going to turn into the probability of A naught and B, and the probability of A naught and C. Again, if you don't like all of these letters, it's okay. We're going to deal with like actual events like red, yellow, starburst, red and yellow starburst. Okay. One way to check yourself is if you add up all of these probabilities, they should equal what number? 1. Okay. So what I want you to do is go ahead and try 1, 2, 3, and 4. You're definitely going to have some type of FRQ where you have to draw a tree diagram. Okay. They like to throw this in there. I think this is a good chunk of your AP exam. Many urgent care facilities offer rapid flu tests that will give results in 15 minutes or less. Suppose that for a certain week in November, the urgent care center in Kentwood, Michigan is visited by many people who get rapid flu tests. For these patients, suppose that 22% of them do in fact have the flu. Okay, so pause. 22% have the flu. The rapid flu test will incorrectly give a negative result for 3.7%. Negative 3.7%, right? Okay, that do have the flu and give a positive result for 2.6% that don't have the flu. Okay, so what are we talking about? We're talking about rapid flu tests. Yes, okay. So we're having rapid flu tests. This will change your perspective on the vaccines, by the way. This unit. So how many of them have the flu? How many of them have the flu? Okay, so 0.22, patient has flu. Okay, that means how many do not have the flu? Okay, so 0.78, patient, no flu. Everybody good so far? So we broke the rapid flu test into they either have the flu or they don't have the flu. Okay, now we have they are positive or they're negative, right? So how many of the people that have the flu, how many of the people who have the flu test negative? Okay, 3.7. So 0.037 test negative. That means how many test positive? 0.963 test positive. Okay. Now, so that means that of the people who have the flu, 0.963 are positive. If we take those two things and multiply them together, then we're going to get 0.2119. If we take 0.22, and we multiply by this 0.037, and that's 0.0081. 0.8% of people who do have the flu will test negative.
Are you trying to make fun of me for everything else for character game?
So she read up here, 2.6% that don't have the flu test positive. Okay, so you're filling this in. So that's going to be 0.026 test positive. That means 1 minus 0.026, which is 0.974, test negative. And then we're going to find the probability that the patient doesn't have the flu, but they test positive. So that means we're going to do 0.78 times 0.026. And that's going to give me 0.0203. For this bottom row, of the patients who don't have the flu, how many test negative? The probability for that is 0.78 times 0.974. And that's going to be 0.7597. And that makes sense. If they don't have the flu, they're going to test negative for the flu. Yeah. Now, again, when you add this up, you should equal 1. That's how you know that you did it right. Okay.
Like the individual, what should
Everything on the ends. That should be 100% of your people. Okay, so we're trying to find the probability that a randomly selected patient gets a positive result. So look at your little tree diagram. Look at your positive results. Okay. What's going to be a positive result? Well, you've got that first little line right here. That's going to give us a positive result. This one's going to give us a positive result. So you're going to add those two together. Add those two together. See what the probability is of getting a positive test result. So you should say 0.2119 plus 0.0203. And that should give you 0.2322. Okay, so I'll scroll up. So again, this is going to be 0.2119 plus 0.0203. And that's going to be 0.2322. Now, if we selected 4 patients at random, what's the probability that at least one of them gets a positive result? Okay, so the probability of at least one is the same thing as saying the probability of none, right? 1 minus what? 1 minus p none. Because we want to see when they don't get a positive result, right? Okay, so looking at our little tree diagram, what would be a negative result? What's the probability of getting a negative result? Well, yeah. The 2 negatives, right? Okay, so combine those two, what do you get? Because we want to find the probability of not getting a positive result. What's the probability of at least one of them getting a positive result from the 4 group? We want to find when it's none, so we can find when it happens. So this will be 1 minus, if you combine those 2 negative tracks, you're going to get 0.7678. Now, how many people are we running this for? So we're going to raise that to the 4th power, because we're doing it 4 times. Okay. When we do that, we should get 0.6525. Say it again. You're not multiplying by 4, you're multiplying by the probability of one person getting it. Okay.
That's for. So.
Why can't this?
Because we need at least with every single one. You don't need that. So now you can be sitting.
Okay,
But if you only need, it's like, well, why can't you use multiple of these?
you can't have more than one.
You don't want just all of them. You want to add this one. So you're not going to push them.
All right, so on the last one, let's go over this quickly. Given that a randomly selected patient is a positive result, so given that they are positive with the flu, how likely is it that they actually have the flu? So the probability of having the flu and they're positive and positive. Okay. So what was the probability of them having the flu and they're positive? Okay, so 0.2119 out of the probability of them having a positive result. We found it in question number 2. Okay, 0.2322. And when we divide that, that's going to be 0.913. Now, again, think about this. If you go to the doctor and you get a test and you already know you have the flu, but they test it, you're most likely going to get a positive result, right? Now, there is a little room for error, okay? These 2 questions probably are the trickiest part of this. This is where we need to practice. Yeah. Remember, your recommended